Hello, everyone. First, I want to thank the organizers to letting me speak here and also letting me visit here. It's really nice, really fun experience, a lot of interesting physics discussions. And today I will talk about collisions of shockwaves in the black hole interior and quantum circuit. It's based on, it's something I've been working on during the past couple of years, and this talk will be mostly based on the last paper. As I said, I encourage questions. I think there's not much background needed. I think everyone should be able to get it. If you are confused by anything, just ask. So first, I want to give some background and motivation. It's well known that two distant black holes can be connected in the interior through the wormhole, if we trust Einstein's gravity. And such an Einstein-Rosen bridge can be interpreted as an entangled state. This is the statement of ER equals EPR. So you'll see somehow the horizon doesn't show up here, and it shows up on my slides anyway. And but there is a horizon here on my laptop, and from the horizon here, you can see that if Alice and Bob jump in, they can actually meet in the interior. And this is a very mysterious feature. It puzzled me a lot. I think it's probably still puzzling a lot of us even at this point. But I will just share with you my understanding. I don't claim that I resolved this puzzle, but I will tell you how I sort of feel like I understand it a little bit better. So here's this is one puzzling aspect. I think there are different puzzling aspects. Two signals sending from the two different boundaries can meet in the interior. On the other hand, we know that the two boundaries do not couple to each other, so there are no boundary interactions. Then the question is that what governs the law according to which the two signals interact? Quite often people will say that when Alice and Bob, people sometimes say when Romeo and Juliet jump in, they will have some good time before dying at a singularity. But if you think about it, how do they even recognize each other? There are no interactions between them. So I will just share with you some of my understanding about this problem from point of view of quantum circuit. Before I start, I should point out that there are some recent work also involving black hole interiors from a complete point of view, from point of view of operator algebra. So before I start, I will just share with you some simplified pictures. This picture is two perturbations spread ballistically through a quantum circuit. This is x direction, this is t direction. And as t increases, it's spread in x direction. And clearly you see that there are two possibilities. In the left panel, there are no overlap between the perturbations, so they do not fill each other. And in the right panel, they do fill each other because there are overlap. And the claim is that so in the right panel, when situation like this happen, the claim is that they will interact gravitationally, and we will try to deduce certain properties of this gravitational interaction from the way they overlap. And from my earlier experience of giving the talk, I noticed that it's actually a bit confusing to show this picture here, because I will first talk about spherically symmetric perturbations in ADS-sized black holes. So in this picture, this vertical direction is actually spatial direction. And later I will tell you that in the first half of my talk, there is no space-like locality, but I'll come back to that later. Here's the outline of a talk. We'll discuss the meeting in the interior of a wormhole and overlap of perturbations in the quantum circuit. We'll discuss collisions between spherically symmetric shock waves in ADS-sized black holes. As I said, I will be happy to stop here. And the next part, localized shocks, it's fun, but it's also more technical. And at the end, I'll point out future directions and unanswered questions. So first, some background, Bock tensor network and quantum circuit. It's argued that the Bock geometry reflects the minimal circuit preparing the state. Here's the cartoon of the quantum circuit. These black lines represent qubits, and these dots represent interactions. You'll see that at each time step, we randomly pair them up, and we apply these orange dots on top of it. And I want to emphasize is that in this picture, there is no spatial locality among these lines. This direction is time direction, but this direction is not x direction, because we are discussing minimal size black hole, ADS size black hole. Roughly speaking, you're talking about ADS patch, one ADS patch, and it's described by matrix degrees of freedom, let's say roughly S qubits. And this naive circuit model is, people made this up to represent black hole dynamics. There are certain features of black hole dynamics. First of all, we know that it's chaotic. Second, we know that it's k-local. From matrix model, people know that it has certain locality, not spatial locality, but in the sense that if you have different qubits, then at each time step, each one of the qubit only talks to a couple of other qubits. So it has some sense of locality and being chaotic. That's why people made this up, such a toy model. This is just for illustration purposes. And later, as we will see, that we only need very little properties from this. Yeah.
Okay, so you might have said this already, but should I think about this circuit as living on that slice?
Good. That's what I'm talking about next. And okay, and as this circuit gets longer, and this interior is getting. Where is thermal field double?
Yes.
I'm representing thermal field double by S-bell pairs, and so these are the horizontal lines represent S-bell pairs. And as you asked earlier, when time goes either from left or right, this circuit is getting longer. The interior slice is also getting longer. And your question is that, do I think of this circuit as living on a specific slice? Actually, my answer is no. At least that's not the way I think about it. I would say that we don't, let's say, look at the Wheeler-DeWitt patch. And there is this direction. We don't have good understanding about locality in this direction. The way I understand it is that this circuit somehow corresponds to the physics here. And, but if we want to ask about the properties, let's say we want to ask how long it is, we use a representative slice. That's why we can take a maximal. Here I try to draw a maximal volume slice, but this is just a representative. But can I claim that it lives on specific slice? I don't want to do such commitment. But the point is that if you want to study the properties of this patch, let's say you can draw a maximal volume slice. Maybe you can draw geodesic. Oh, geodesic probably is not good. But there are other quantities. Let's say you can, in 3D, you can definitely look at geodesic. And, or you can look at space-time volume. They would show certain universal features. And those universal features is what we will be interested in. So I don't think about living on specific slice, but you can think about that this, roughly speaking, this interior part. Again, somehow the horizon doesn't show up here. So I actually draw two horizon lines here. And this yellow part is inside the horizon. And as time increases, this part gets longer. Another question I got from previous talk is that where is exterior? Exterior is not shown on this tensor network. This tensor network basically only represents the interior. That's why we only have S qubits. If you want to represent the jump in the exterior, you need much more than that. Here, we only happens. So for the purpose of this talk, we're only interested in what happens in the interior.
So the top field double is just a line without any gates.
Yes, exactly. And one key property is that if you play with this a little bit, you notice that if you have maximally entangled pairs, then actually it has a property that all these gates can be undone from either side. And this has some interesting consequence. Let's say Alice and Bob share such Bell pairs, and Alice applies some gates on her side. And then she left her lab. And later Charlie comes in, and Charlie looks at the system. There's no way Charlie can tell if Alice ever applied these gates or not. These gates basically makes no sense for Alice's subsystem alone. And these gates also makes no sense for Bob's system alone. But when you have Alice and Bob system together, you can actually study the system and see that, oh, Alice once applied these gates. That actually corresponds to the property that this, unfortunately the horizon doesn't show up. That actually corresponds to a property that this orange slice somehow is inside the shared interior. For those of you who are familiar with the subregion duality, it's a well-known fact in this case that the left exterior belongs to Alice, the right exterior belongs to Bob, but the shared interior only makes sense when you have both subsystems together. You see that certain properties of this subregion duality actually has a nice correspondence with the property of these quantum gates. These quantum gates only make sense when you have both subsystems together. So that's one thing I learned. Once you have entanglement, you have shared quantum circuit. It's really shared, as we will emphasize this later.
Is that circuit supposed to be dual for the entire spatial slice?
As I said before, first of all, it's only the part inside the horizon. And the way I think about it is that I don't put it on any specific slice. I would try to, as later we will discuss, I will try to get some physics in this region outside the property of this surface. I don't know exactly which slice it lives on. I think for the simple reason that once you have Wheeler-DeWitt patch, this direction basically is of ADS length, and we don't really understand its locality. So here is, so far is unperturbed thermal field double. Then we try to study perturbed thermal field double. The way we do this in the circuit is that we imagine there is some extra qubit. And just think about this extra qubit, because the dynamics is chaotic. So think about this extra qubit as some extra guy that carries some disease. And then you see that its effect is basically well spread throughout the circuit. The detail doesn't matter, but there are certain properties I think so far, unfortunately, all of us are too familiar with. First of all, this disease will spread exponential in time. Second, well, eventually it will saturate. That's basically the only properties we will need. And you may ask, why do we introduce extra qubit? The reason is, as you know, that if you apply an operator, let's say on one side, on the left side, you know that the black hole coarse-grained entropy will increase. This extra qubit basically represents this coarse-grained entropy. And now clearly from the picture I draw, you see that now there are two kinds of gates, the orange gates and the red gates. And here we'll make assumption here is that these red gates, because they involve this extra qubit, actually can no longer be undone from Alice side, from the left-hand side. I mean, this is assumption, but I hope it sounds reasonable because simply because this line, this extra line only belongs to the left system. It doesn't belong to the right system. But I won't use too much about this property in this talk. What I will use is the fact that there are still, let's say, the perturbation come in at this time. But even after this time, there are still orange gates. And this really is a property of a k-locality of the dynamics. Because the perturbation takes time to spread. It's like when COVID first hit, there are always healthy people. It's because this is really a result of k-locality. And one lesson learned from here is that the fact that black hole dynamics is k-local actually is closely related to the geometry. Because we will see that what we will do is that we will identify these orange gates after it come in to this part of the geometry, this orange part. This orange part, you see that it's after the shock wave. It's on the left-hand side of the shock wave. It's affected by the shock wave. But it's still healthy in the sense that, again, the horizon doesn't show up. But I assume most of us are expert on Penrose diagram. You know that secretly there is a horizon here. So the orange part is actually still in the shared interior. So it's still in the shared interior, it's outside the entanglement wedge of A, it's outside the entanglement wedge of B. It's still shared, but it's actually after the collision comes in. So that's really a result of the fact that black hole dynamics is k-local. Yeah.
Sorry, can you say again why the pink thing is not in the shared interior? What is shared interior?
The shared interior, okay, unfortunately the horizon doesn't show up. Let's say the RT surface is the blue dot. The shared interior is the region that outside the entanglement wedge of both A and B. And this red part, it's in the interior. It's in the black hole interior, but it just belongs to Alice. It doesn't belong to Bob. And let me see what I'm going to talk about. Yeah, this is a consequence of k-locality. Okay, I will talk about two perturbations, but before I talk about two perturbations, I think it will be helpful for me to try to attempt to very quickly explain something here that once we have a circuit like this, let's say I slice it somewhere. What does this slice mean? That's, I find something interesting. Without any perturbation, here's the Penrose diagram you get. And basically, you have time translation symmetry if you jump in here and here. You also have time translation symmetry if you're jumping at different times on the right. And I would say it corresponds to slice it this way, no matter you're jumping from left or you're jumping from right. This should be intuitively clear. So I can identify this kind of slicing with this kind of slicing, or I can identify this kind of slicing with this kind of slicing. The point is that this circuit is really shared between Alice and Bob. But once I perturb it, there's something interesting. Once I perturb it, what?
I consider jumping in from the left at later and later times.
Yes. Correspond to different slices of this circuit. Yes, towards the left. Because the left dynamics go towards the left. Yes. But let's say I throw in a perturbation at some time. And the Penrose diagram will be something like this. The claim will be that you actually can still sort of, I want to claim that somehow to a certain approximation, the experience of an observer, even no matter you're jumping from left or you're jumping from right, is still encoded in this circuit. Here's my interpretation. Let's first look at a left observer. A left observer will pass, let's say, on his or her trajectory, he will pass a region where just belongs to Alice, and also will pass a shared region. So correspondingly, what will happen is that you slice it this way. There will be some gates. There will be some gates that actually belongs to Alice alone. It's this part. There will be some gates that is shared between Alice and Bob. That, roughly speaking, correspond to this part. You can make it more quantitative. But what happens is, imagine that if you're jumping at a very late time, what will happen? If you're jumping at very late time, you no longer meet healthy gates. All you have is that you are jumping into a black hole where it completely belongs to Alice, which corresponds to the fact that you only see this kind of red gates. And what I find more interesting is this. Let's consider a right observer, Bob. Bob can also jump in at different times. But for Bob, as we emphasized before, Bob can only see these healthy gates because these red gates belongs to Alice. But what we see is here that as in this circuit, as you move towards the left, the number of gates Bob can see becomes smaller and smaller. Let's say here Bob can see a constant number of healthy gates no matter what time he jumps in. That means correspond to he jump in here. He basically will miss the shock wave. And once he passes this time, he will meet some kind of these sick gates. He will only see this part of healthy gates. But the number of healthy gates, as you move in this direction, becomes smaller and smaller. And eventually, there's almost no healthy gates. And there is one computation you could do, a simple computation. You estimate the proper time Bob experience from enter the horizon to hitting the singularity as a function of a time where Bob jumps in. You indeed see this kind of behavior. Initially, here, Bob just doesn't feel the shock wave. Then Bob starts to feel shock wave. Eventually, once Bob jumps in early enough, it's not obvious in this Penrose diagram, but if you carry out the calculation, you will see that the singularity actually bend towards the shock wave. If Bob jumps in really early, he basically passed the shock wave and immediately hit the singularity. And it's reflected to the fact that there are basically no more healthy gates for him to experience. So in this sense, this circuit is really shared between them. They have different point of view, but both of them can read out some of their infalling properties from this circuit. So far is done for one observer. Any questions? What will be interesting in this talk is a property when we have two perturbations, one from left, one from right. And if you have two perturbations, you draw the circuit picture. Clearly, you have two possibilities. From the range of the time, when the time is arranged this way, then they do not have overlap. And correspondingly, the proposal is that the signals sent in into the bulk hit the singularity before they have a chance to meet in the wormhole. The more interesting case, obviously the case is that you arrange the time such that this portion, they have overlap. I think there is one confusing factor about this picture is that from this picture, it looks like they don't talk to each other. I know that this is confusing for some people, but this is a defect of this naive toy model. Because in this naive toy model, it looks like someone comes in, only affects one other guy, only affects that, only affects four other guys, things like that. But imagine when you have a continuous Hamiltonian evolution and you perturb it, what will happen? What will happen is that this thing will affect everyone else after one time step, but only a tiny bit. And then gradually it affects it more and more. Yeah?
Yeah, I didn't understand this earlier, because why are you drawing these gates as nearest neighbor gates when I think you were specifically saying that that's not what you want, right? You want.
Because I don't know how to draw the picture otherwise for Hamiltonian evolution.
You was saying that the interactions are k-local, but
Yeah.
you shouldn't think about them as like this. You should think about this spatial arrangement as corresponding to the geometric
Yeah.
arrangement of.
Yeah, but let's say they're too local, right?
Yeah.
Then I still would expect that sometimes you have nearest neighbors and sometimes you don't.
Oh, sure, yeah.
It's not.
Yeah, and you see that at each time step, I actually shuffle these lines.
Yeah.
So this is
But
really,
maybe I'm missing what would have been bad about drawing it sort of the way you actually mean it. What will go wrong with that?
yeah, well, so what's the suggestion? This is really a toy model.
Normally people draw these like lines that show where the 2-bit gates connect, and then sometimes the nearest neighbor, sometimes they're not, and then things spread out according to that.
Yeah.
So
Here,
you can see here that there's an interaction.
oh, here the model I had in mind is that I have S qubits, and at each time step, I shuffle these S qubits. I randomly pair them up, and each pair I apply a 2-qubit gate. And next time step, I reshuffle them, I repair them, and on each pair, I apply another 2-qubit gate. I
For
think,
example, if you just put something one,
yeah,
then you have only less than half,
yeah,
but even that less than half may contain a qubit which is already affected.
yes, yes.
But this diagram doesn't.
Yes, yes, yes. I think this is really a sort of, it's a defect of a naive toy model. It's also it's my limit of drawing this picture.
I think it's a need to draw it.
Yeah,
Not
but
many to draw.
yeah, but as I said, as you will see later, that the physical property we read out of this really is we need exponential growth, we need saturation, and I think it's probably reasonable to accept that even we know that real black hole dynamics is is a continuous Hamiltonian evolution. But some notion of exponential growth and some notion of saturation must be there. You look very unhappy, Raphael. It's
No, there's something that's confusing me from the beginning, which
Yeah.
is the relation between tensor networks and these quantum circuits.
Yeah,
I think in a tensor network, one thing that makes it easy to think about is that I can read it sort of in any direction.
yeah.
You know, I can. So.
Oh, by the way, there's no locality notion in this direction. I'm thinking about this as a cable. This cable roughly corresponds to one ADS patch.
Yeah.
And this direction corresponds to this direction.
Yeah, so that's just like saying that every time step here is
Yes,
a
yes.
big tensor. I mean,
Yes.
you just can say that all of these, that the bond dimension is large.
Yeah, the bond dimension is large. Exactly. Yeah, exactly.
But without the perturbation, I could think of this as a tensor network that just has no dangling legs and prepares the two boundary states.
Yes, exactly.
I could also, of course, think of it as a quantum channel in which I project one boundary to some state and then it propagates to the network.
I wouldn't say that I project this on a specific state because these are entangled.
Well, what I'm trying to understand is your rules for what happens when you add. Is this like what you're doing now? Is this like adding dangling legs? And why you're.
I didn't add dangling. I start from S-bell pairs.
Yeah.
Then I introduce one extra qubit.
Yeah.
I basically introduce extra thing to the system, but this extra thing only belongs to the left side.
Yeah, that's the part that I mean, I see how you have to draw it that way to make contact with the space-time picture.
Yeah. And I think physically
what
would.
follows from the quantum circuit picture, or what forces me to do that?
Oh, physically what happens is that for unperturbed thermal field double, the coarse grain entropy equals thermal entropy, equals entanglement entropy. And we're represented by S-bell pairs. And now I perturb it. The coarse grain entropy of left side actually increase. That means it will be larger than its entanglement entropy. You see that there are S+1 lines on the left, but only S lines are connected to the left. You can imagine this guy as something that initially is in the vacuum state on the left. You didn't excite it. Now, as you apply an operator on the left, you excite it, and it starts to participate in the black hole dynamics.
But I could excite it to a pure state, right?
It's trying, yes, exactly, but we were trying to, it is in a pure state, in the sense that this guy is not entangled to the right.
Yeah.
Yeah. So when this guy comes in, it's not entangled to the right.
But the reason that you're evolving. I'm really confused about why we how to think about this from the quantum circuit viewpoint. The quantum circuit to me is like something I use to evolve a state from one end to the other of the circuit.
Yes.
Here it's something that
I start from here.
Finish my question.
Yeah.
Here it's something that I'm not allowed to think of that way in the thermal field double itself. I'm more supposed to think of it as a tensor network that prepares the state. But then when I add some extra bits, now I'm supposed to think of it as evolving something to the left and the other thing to the right. Somehow I'm finding it very hard to connect that with how I normally think about quantum circuits.
So let's say the way you normally think about quantum circuit is you start from initial state, then you evolve it, right?
Yeah.
But I'm allowed to start from a thermal state,
Yeah.
right? So how about, let's say, I have some bell pairs,
Yeah.
S bell pairs. Let's say from Alice's point of view, what does she have? She has S qubits in thermal states.
Right.
Now she can run her quantum circuit. And it starts from a purely thermal state, it goes.
There should be a preferred slice through that quantum circuit that represents the original thermal field double.
Good question. It's let's say this slice,
Yeah.
and then I can apply this kind of gates. I can also apply the gates here.
Exactly. Then you can grow it up. But you never showed that slice on your slides. Maybe that's
Okay, if you ask what this slice is, I would say that you can say ask, but the question is that this portion of circuit, I can cut it here, cut it here. Because if I want to specify pure state, I need to cut it at 2 different times. How about that?
okay. Can you just say where that slice is? Where's the slice?
Oh, it's this slice.
I know, but on the common circuit, I mean.
At the center, at the center.
Is it at the center?
Yeah.
Are you asking me? Are you asking me that if I slice it here,
Where's t equals 0 on your quantum circuit?
where is t equal to 0?
You automatically at the center, of course. Depends on where you set the origin of TL or DR, but some slides.
I think it's easier if we consider 1 perturbations. So without perturbation, it should be clear that any slice here, it's, I can consider it as when this guy is really short,
Yeah.
it corresponds to this slice.
Yeah, I'm not. You keep telling me what the t equals 0 slice looks like in the geometry.
Yeah,
That's how I'm defining it.
yeah.
I'm asking where it is in this diagram. I think it should be through the center, like as you're saying. But I'm
No, the question is that
I'm confused why you're then drawing the gates so like that should be one slice where the gates look like you just start with an entangled state.
Yeah.
And then you keep growing it out.
Yeah.
I'm sort of, I think it would have, yeah. Maybe that's all that's missing.
Oh, I see. Somewhere in the middle, but somewhere in the middle. But from left point of view, you need to first evolve to the right, then apply a perturbation, then to the come to the left.
To the past.
Yeah, and for something here, you need to first evolve to the left, come to the past, then evolve it towards to the right.
Okay.
So with this motivation, of course, there is no geometry double.
Yeah.
But
Am
it's just
I thinking of this as a spatial picture rather than just say we have t equals 0 and then the evolution happens on the boundary, just going forward, like
Ye-
in time?
Yeah, but then you bend the boundary time evolution to the horizontal slice. That's what you get.
Yeah, but that just what do I gain from doing that other than being confused about space and time? I mean, having to translate space into time all the time. Keeping track of which side I'm on and which side I
I will try to. So the question is that what do I gain from that?
Yeah.
What I learned from this is that I will read out some properties of the interior from this. Let's say I actually already showed you some properties of the interior. Let's say I notice I can see how this region grows with time, how this region grows with time from just the gates counting with 1 perturbation. And I can estimate the proper time Bob will experience after jumping in from just the circuit analysis. And of course, it will be more interesting once we have 2 perturbations, if you ask what we gain from this. The point is that, at least the way I understand it, is that, okay, this is so unfortunate the horizon doesn't show up. The interior geometry,
I can visualize that.
yeah, the interior, I'm sure you can visualize that. It's, the interior geometry somehow, it's like you can, the one lesson I learned from this series, from studying this, is that certain effective field theory properties of the interior can be encoded in this quantum circuit. That's what I try to convey. And maybe ask me later, see if I convey my message once I show you more properties that I will try to study the properties of this collision. And I want to show that how the property of collision, on one aspect, you can certainly study it in GR. On the other aspect, just study this part of a circuit. And I will try to make a match. That's the goal. it's true that the dynamics is the boundary dynamics. And if you ask me, why do I bend it horizontally? The first answer I bend horizontally is years ago, Wang and Lenny bent it horizontally. The second answer is that after I bent it horizontally, I learned that I can read out interior properties from it. So this is the, okay, I think I will just stop in the middle of that, but I will be really happy to do that. So there is a situation like this when the two perturbations do have an overlap in the quantum circuit. Correspondingly, we want to argue that when such a situation happens, we want to argue that they actually collide in a wormhole. And it should be intuitively clear that the larger the overlap is, the stronger the collision is. And actually, one can diagnose how large the overlap and how strong. I can diagnose how strong the collision is by estimating how large the overlap is from a boundary point of view. It reduced to a computation of certain 6-point functions, but I'm not going to talk about it in this talk. So I think I have 20 minutes left. I just want to convey the message that how to read out property of this part, post-collision. The one property I'm interested in is what's the geometry of a post-collision region? What happens after the collision? And I want to argue that it's related to this part of the circuit. So let's look at in this overlap, there are still some orange gates here. This orange gate has two properties. First of all, they are orange, so they are healthy. Even though there are two disease spreading, but these are the lucky guys who stay healthy. The second property is that because they are in this overlap region, they somehow are affected by both perturbations. So they are after both perturbations come in. So we will try to identify the number of gates, the number of lucky guys here with this region of space-time, post-collision region. That's the simple proposal. Then let's, yeah. Why? First of all, because they are healthy, so they must be in a shared interior. This is criterion number one. The second criterion is that they are in this overlap region, so they must be after this shock wave, also after this shock wave. And the only region you have is a post-collision region. And to simplify things a bit, it should be clear that, so what we do is that we will analyze this property. We will also analyze property. But it should be clear that everything is only a function of this time difference. From circuit point of view, this is the translation symmetry of the circuit. From this point of view, from the bulk point of view, that's the boost symmetry. And from quantum circuit analysis, let's actually, because I don't have enough time, so it's not necessary, but let's say we can consider the initial strength of two perturbations. Let's say for the left perturbation, initially I send in one sick person. For the right perturbation, I initially send in square root of s sick person. It should be clear that the left perturbation will take longer time to saturate comparing with the right perturbation, because the right perturbation has a worse initial condition. It has more initially sick person. And so in this case, the scrambling time of this guy is longer than the scrambling time of this guy. And I will no longer draw this kind of picture because I couldn't draw it. Felix can draw it. I will use this kind of picture. I think the meaning should be intuitively clear. And let's first do circuit analysis. And it's fairly simple. Just draw pictures. You'll see that there are 4 different regimes. One regime is that when delta t is really small, as you make delta t larger, the healthy gates here are shown in white region here. What will happen to this white region? This white region, roughly speaking, grows linearly in delta t. And in the second regime for me, it's a quite interesting regime, is that when delta t is in certain region, which is between the 2 scrambling times, actually the overlap, the healthy gates in the overlap no longer depends on delta t. It plateaus. I mean, this is a highly non-trivial. We'll show that this is a highly non-trivial property of GR, but from circuit, it's really simple. So we see that the number of healthy gates there as a function of delta t is that initially grows linear delta t, then it plateaus. And then as delta t further gets larger and larger, you see that this part starts to shrink. It also shrinks linearly in delta t. At the end, when delta t is really large enough, is larger than, let's say, 2 scrambling time, they're basically no more healthy gates. I mean, this is a really cartoon circuit model. As I said, I will only use minimal properties of circuit model, exponential growth and saturation.
Sorry, gravity side?
Gravity side, I will come to gravity side. I will come to gravity side. So the question is that what properties of a gravity side give you rise? There are 2 effects in gravity. One effect, you imagine, for now, ignore back reaction, just 2 signals propagate on a fixed background. As delta t increases, this colliding point will move down, and this part will grow. This is one effect. The second effect is that as this collision becomes strong and strong, as we mentioned earlier, the singularity actually bends towards the shock wave. That will make this region shrink. So what ends up happening roughly is this. In the first regime, it's the first effect dominate. This is when the second effect dominate. And this is when the 2 effects just cancel. I have to admit that when I first noticed the existence of such regime in the circuit model, I was worried because there's no guarantee that gravity will produce a plateau. But
So how to make the scrambling time different?
Oh, just the initial strength of perturbation. Let's say let's say initial, I throw in different amount of epidemic, or in physics terms, throw in different amount of energy.
Can you say again the number of healthy gates you identified that with the amount of time I survived for on site?
Let's say I will try to emphasize. So the question is that I identify the healthy gates. My picture is that the number of healthy gates is stored in this region. So the very naive question I want to ask, I want a quantity to estimate how large that region is. Yeah, so I just computed volume, but I'm pretty sure you can come up with other quantities because, as I said, I don't think about it as on a specific slice. I just want to estimate how this size grows or shrinks with time. I mean, the simplest thing to quantity is its volume. So one can indeed do this calculation. It's the simplest to do it in BTZ, and here is what we get. I think you can actually see that each line are actually secretly 2 lines. One is a dotted line, one is a solid line. The dotted line is from gravity calculations in BTZ. The solid line is from circuit model estimate. And as long as there is a hierarchy between scrambling time and thermal time, they match surprisingly well. And I have to say that especially this regime, when there is a plateau, it really came as a surprise for me. Somehow these 2 effects managed to cancel each other pretty well. So that's one property of the post-collision region we can learn from circuit analysis. I hope this can answer your earlier question, why do I bother to do that? I want to claim that this naive quantum circuit encodes some effective field theory of the gravity. And this is a specific aspect, it's gravitational interactions between 2 signals. And I think I have 10 minutes. I really don't want to rush to localized shock waves. I will just summarize, then go to the, and then conclude. Then I will welcome more questions. So before that, I would say that you can do this in more complicated setup, in localized shock waves. Maybe I'll just show you 2 pictures. In localized shock waves, there is a quantum circuit picture that's given by these guys. Roughly speaking, okay, so in this picture, this is actually spatial direction. And you have a signal coming here. Basically, it's characterized, the propagation of the signal is characterized by 2 cones. And this is the light cone. This is speed, the slope is 1. This is speed of light. Clearly, the effect, it only affects anything that happens here. And you have another cone, which is a butterfly cone. The statement is that the effect stays exponentially small until you reach the butterfly cone. And the butterfly cone, the slope is actually not 1. The butterfly velocity, it depends on dimension. But roughly speaking, the circuit picture for just one perturbation is look like this. And I will show you this picture again. So you just do some complicated thing. As I said, it's I will skip all of this. I just want to show you at the end basically this picture again. Higher dimensions. Okay, here. So this plot is about a case where you studied head-on collision. And this is a 3D plot. This direction is x direction. This direction is I fix the left time, I vary the right time. It's a kind of, I have a head-on collision, so there is a left signal that propagates here. And I also have a right signal, basically head-on collision. That means it happens at the same x, but I adjust this time. I adjust the right time when the signal comes in. So this is the right time. I fix left time, adjust right time. Basically, I adjust the relative time difference. And the height of this tells you the number of healthy gates at a specific x. So you see that if you fix a constant x, you basically get what we expected. You have linear increase, you have plateau, then you don't see that there is a linear decrease, then stays exponential small. But as you go from as you're away from, so clearly this is the center of collision. As you move away from the center, this entire curve is actually shaped. The reason I want to show you this curve, you may not get the detail of this curve. It doesn't really matter. I don't expect you to get it. But the reason I want to show you this is because of this. This is a top-down view of this picture. It should look very familiar with the circuit picture I just showed you. There are two cones. One is controlled by the speed of light. The other is controlled by butterfly velocity. Now if you do a top-down view of this, you automatically get this. But this plot is not from circuit analysis. This plot is, we got this plot by studying the properties of a post-collision region in the interior. And somehow you see the properties of this, the circuit property automatically shows up. That's why I want to show you this plot. It's you get the same circuit picture from studying the interior post-collision region. So in the last 5 minutes, I will just point out some future directions and unanswered questions. So for us, the property is to get a boundary interpretation of bulk gravitational interaction, in particular bulk gravitational interactions behind the horizon. But we immediately encounter one question. What is the right bulk quantity to ask about? Because it's behind the horizon, it's not something people studied before. So normally when you talk about gravitational interaction, what do you have in mind? Newton's law, maybe fancier thing, S matrix. But in this case, there is no asymptotic out states. You have asymptotic in states, but you don't have asymptotic out states. So how do you define S matrix? S matrix naively just doesn't work. And so far, what we studied is the post-collision geometry. What's the lesson we learned here? I don't know. Maybe at the end of the day, that's the right quantity to ask. That's the most natural thing to ask, but maybe not. So that.
You can probably do something informally, just to compute the correlation or something.
Yes, exactly. That's what I want to say. So there are two directions. In terms of future work, there are two directions I have in mind. One direction is this. Let's say consider ADS Rindler. From one point of view, I can treat this as a planar black hole, actually hyperbolic black hole in higher dimensions, hyperbolic black hole. I can study collisions in this hyperbolic black hole and ask about various properties from circuit analysis. On the other hand, I know that as long as the collision is not too strong, the signals actually secretly come out to the boundary. So I can also study the process from more traditional point of view, like correlation functions, S matrix. So I would like to make a comparison with this different approach, see what happens. Another direction I find interesting is this. So when you do circuit analysis, you actually see a very sharp transition here when there's no more healthy gates. And what it corresponds, this roughly corresponds to case when G squared S of order 1 in different dimensions with actual powers of LADS. And let's say in case of regular ADS, what it corresponds to black hole formation, real black hole formation. So we are treating this as a regular black hole, but real black hole formation. So basically signals can no longer reach the boundary. But there are some solutions that are studied by people in 3D about this kind of black hole formation. So I would say that this part is poorly understood, but one can maybe try to understand this part from circuit point of view with the property of black hole formation. That's potentially another direction. And these are also some unanswered questions. I find them very interesting. They're really hard. I have no idea. I'm happy to discuss with people. Let's first, the role of singularity. The existence of space-like singularity prevents the... So first of all, I want to say that I do learn something about the singularity from a very naive analysis here. Because what I learned from here, let's say one shockwave, is that somehow, let's say you have perturbation like this. What do I learn? I learned that the proper time someone jumps in is if you want to estimate, just count the number of healthy gates here. If you don't have healthy gates, you immediately hit the singularity. So it looks for me that when you don't have healthy gates, you directly hit the singularity. That's one lesson I learned. I don't know how general this is, but I find it interesting. Another issue is this, that throughout this talk, I actually lied a little bit, because all this, what I said, only works when you have a space-like singularity. If you have a charged black hole, if you really trust the smooth inner horizon, they can always meet no matter what. And I find this a very puzzling feature from circuit point of view. So,
but why don't just people say that's...
Yeah, maybe. The question is that how space-like that thing is. So singularity is puzzling, but what I find that the missing singularity is even more puzzling. And so the collisions near the inner horizon here, it's something I have no understanding about. That's one puzzle feature. And another puzzle feature that, so let's say we want to say that somehow the effective field theory in the interior can emerge from this quantum circuit. But then we want to ask what happens when the circuit becomes exponentially long. This amounts to ask the question that what will happen to a black hole if you evolve it for exponentially long time. And there are different proposals. I think many of you heard. Yes, none of them are well tested, so I don't know. And we've been trying to understand ordinary matter propagating in this background. And what about firewalls? It's interesting that in this regime, that when you jump in, you first of all hit a high energy collision. You also immediately hit the singularity. So I don't know if it can help us, give us any understanding about firewalls. At the end, it's throughout this set of work, I had a fixed Hamiltonian in mind in the context of ADS-CFT. Then, is there any way to incorporate different states of baby universe? Is there any way, I mean, Misha gave us a very interesting introduction about topology change. Is there any way for the circuit model to incorporate anything like this? I expect that it actually will relate it to, if one really try to answer the second questions, it might be related. So these are the unanswered hard questions. Yeah, that's all I have. Thank you. Yeah.
So on the second point about late times.
Yeah.
I mean, in their model, isn't it that you just get more qubits, whereas here it would be like you're making a longer.
In whose model you get more qubits?
Sorry, the one by Chris and Daniel.
I think what do you mean? I think their model breaks down at exponentially long time. And it's so what I learned. I put the two works, the two recent works here. What I learned from the first work is that at exponentially long time, this bulk to boundary map, this encoding, becomes a badly non-isometric. And what I learned from the second work is that somehow it can, by non-perturbative effects, it can tunnel into a shorter wormhole. So in some sense, in some very vague sense, the circuit can actually cure itself by going to a shorter one. So that's just the separate lessons I learned, but I don't know how to put them in a coherent story.
For the first one, it's kind of obvious in the sense that if you have e to the s,
Yes, exactly.
you have only e to the s.
Yes, it's obvious, exactly, yes.
The second one is more.
Yeah.
I just had a comment, I don't know how useful it will be, but on the question of the charged black holes.
Yeah.
So, I mean, as I'm sure you know, the only case that you actually have to worry about is the unperturbed case.
Yeah.
The observations very quickly make the singularity space-like.
Yeah.
But even in the unperturbed case, Arvin and I found, well, sort of indirectly, that we should probably replace this with a space-like singularity in the following sense that.
That would be interesting.
Well, we found that there are other situations where the semi-classical approximation, you have to define when that is good.
Yeah.
And we have some evidence that the way that you have to define it includes rejecting certain slices with large extrinsic curvature.
Okay.
And the extrinsic curvature diverges for these slices even in the unperturbed case. And so even though we can draw this nice smooth geometry there, there's probably a well-defined sense in which that's just not a good. So if your slices are anchored to the boundary,
Yeah.
then you cannot approach the inner horizon arbitrarily closely with slices that have low extrinsic curvature, and therefore, if your definition of semi-classical approximation is like ours, then that approximation just breaks down before you have the problem that you identify.
Okay, that's good. Thank you. I have to admit that, so let's say I'm trying to push this effective field theory in the interior from circuit. There are two difficulties or two potential problems here. One potential problem is that a circuit model is discrete, it's a toy model, and the real dynamics is continuous, is a Hamiltonian evolution, so there might be some limit. But I consider this as a less serious problem. The more serious problem is that, let's say, interior with charged black hole, the interior is this part. With the uncharged black hole, the neutral black hole, the interior is this part. One thing I'm confident is that if you are close to the horizon, then the circuit the result circuit gives you is impressively accurate. But the question is that if you go away from the horizon, as you close the singularity, do you need something else in principle, going away from the circuit? Actually, after I came here, when I talked to more people, I sort of started to tend to think that maybe the answer is yes, simply because we know that somehow no matter the properties here or the properties here are more sort of sensitive to the UV data of the boundary theory. And this circuit is an IR object. So the way sometimes I think about it is that we discuss, let's say, the trajectories here. We more or less identify the trajectory here with something like this. But we need some UV information here. So I don't know how to put all of them together. I think that's a more serious issue. It's just to understand the interior closer to the singularity, what do we need?
Just quantitatively, if you were to put in a cutoff at some large value of the extrinsic curvature, would everything still match?
Let me see. Where is that? Can you tell me where is?
So if you just put I can't tell you exactly, but yeah, if you just replace it.
Yes,
Maybe it bends up a little bit or something, but it probably doesn't matter. Right?
Yeah, if you put it cut off here, then yes, I think everything works pretty good. Because if you cut off, let's say, at the horizontal line, that's exactly the case that when they have the equal time, they meet. And when you go into the past.
Yeah, but how bad does it get if I bend this line up a little bit? I mean, do you really care? Or?
I do care.
Oh, okay.
If it bend up a little bit, I would say that I would lose the very sharp diagnostic about meeting versus no meeting. So the question is that this transition is fairly sharp, but this transition is mild. So if you consider the 6-point function that we used to describe a meeting versus non-meeting, it has the form like this.
I thought that you were going to identify the number of unperturbed gates with, or clean gates,
Healthy.
With some 4 volume.
Yes.
If we're worried about that,
Yeah.
shouldn't that smooth things out in a way that?
I think so. It will. I think so. It's one issue. Another issue is that so far what I considered are too crude, in the sense that I only considered space-time volume. I think the properties like this will be sensitive, will be more sensitive to exactly what quantities.
But maybe this approach has an error bar corresponding to LADS. Wouldn't it be okay for it to have that error bar? You're sort of discretizing the space-time effectively into ADS.
Yes. I thought about this, but on the other hand, we do consider the fact that this point is moving down, and this is within an ADS patch. So, and the circuit model, it's like we already are discussing those matrix degrees of freedom. So I don't expect that it gives a good description of inside ADS patch. But I think I agree with what you said, that there are error bars here, especially when you are in this region. But I would say that it's not completely ignorant about LADS, but it's also not good enough. In particular, for the region we are really interested in, it's not too sensitive to what happens here. Because the volume growth or whatever, most of the things actually happens near the horizon. So this is a very big question mark. If anyone has ideas, that would be great, and we can discuss more.
All right, well, if there are no further questions, let's thank